Okay, now we're going to talk the photoelectric effect. And the photoelectric effect is something we've known about for a while. We're going to calculate the energy of a photon, kind of review over that, and then we'll explain and do calculations with the photoelectric effect. Now, the photoelectric effect problem, and again, we had known about this for a while. We knew that electromagnetic radiation striking some metals may emit electrons. We call those electrons photoelectrons because they're being emitted by light. Photo means light. But we realized that not all electromagnetic radiation created the electrons. Now, a higher intensity light, for example, a brighter light, doesn't affect whether electrons are emitted. So if you have a solar cell and that solar cell will not work with red light, a brighter red light is still not going to cause it to work. But a higher frequency light would. So if you then put it under, say, purple light, which is a higher frequency, then the electrons would start being emitted. And we didn't really understand how that worked. Now let's review over things kind of quick. Quantities of light. The smallest piece of light are called a photon. Again, it's a packet of light energy. It has no mass, it has no charge, and it travels at the speed of c, 3 times 10 to the 8th meters per second in a vacuum. Energy of a photon is given by the equation E is equal to NHF. N is the number of photons. H is Planck's constant. Again, there's 2 different ones you use, and F is frequency in hertz. So let's review and do a couple sample problems. What is the energy of a single photon of microwave energy if the frequency is 2450 megahertz? That's a common microwave frequency. You can find the frequency of your microwave by looking on the back of it. E is equal to HF. Now, since I didn't specify, I'll go and use the 6.6 times 10 to the negative 34 number times 2450 times 10 to the 6. Remember, mega is a million. So I get 1.6 times 10 to the negative 24th joules. That's the energy of a single photon. Now, to calculate the energy of 50 photons, I simply multiply that number times 50. 50 times 1.6 times 10 to the negative 24 joules is equal to 8 times 10 to the negative 23rd joules. I simply have 50 times that amount. Excuse me. Now again, and here's the shortcut we made earlier. E is equal to hc over lambda, and hc are constants. So again, it's a shortcut because now you can do it directly with wavelength. What is the energy of a 3 centimeter radio wave? Well, E is equal to hc over lambda since they gave us the wavelength. Now in this case, I'm going to use the meters one. 1.99 times 10 to the negative 25th joules times meters because I got a radio wavelength in meters. Of course, it's got to be 0.03 meters to make my units work out. I get 6.6 times 10 to the negative 24th joules. So now what is the energy of a million of those? So therefore it would be a million times that. So 1 times 10 to the 6 times that. So I get 6.6 times 10 to the negative 18th. Now remember, when you add and subtract, adding and subtracting integers on times 10 to the negative 24th and times 10 to the 6th, you simply add them when you're multiplying. Now, the spectrum of an excited hydrogen atom is composed of blue, green, red, and violet light. What property determines the energy of the colored line? Later we'll talk about why that happens, but right now I'm just telling you that that does happen. So what determines the energy? Well, E is equal to HF, so therefore obviously frequency has to be the winner. Frequency determines energy of light. X-rays have more energy than red light does. What is the significance of the slope of the graph as shown? And this was actually used to calculate this number. Rise over run, so it's E over F. H, winner. Because E is equal to H times F. So H is the slope of that graph, and that was actually how it was calculated. They plotted the energy versus the frequency and got that. Now, Einstein's theory on the photoelectric effect, to solve it, and these are some of the drawings that he did, obviously added color and all that stuff. He said the electrons in the metal are held by essentially an energy well, like a dip that kept the electrons in place. So the electron must absorb enough energy to get out of that dip. So the electrons had to absorb a single photon with that minimum amount of energy, and that's known as the work function. Any excess absorbed energy became the electron's kinetic energy and caused it to move. So in other words, if I get just the right amount of energy, I get it up to the top of that well. To get it moving away from that well, I had to have excess kinetic energy. I like to think of it as a more common way to do it. To me, makes sense is you want to go to the movie. Your parent's the incoming photon. What that means is that they're going to provide you energy. You are the photoelectron. You're in the metal. The ticket price is the work function. Any extra money you get is kinetic energy. So your mom gives you $20. The ticket costs $8. $8 is the work function. In other words, they don't let you into the movie if you only have $6. You have to meet the ticket price in order to get in. If you have any extra money left over, you can buy popcorn and all that stuff. So therefore, it's kind of like your parent is the incoming photon. They provide the energy that you need. Hopefully, if they don't, get a job. And then you're the electron sitting there. And again, you don't get in unless you meet the work function. So the work function is what it takes to remove that electron and get it moving. Anything above that will give you extra kinetic energy. So if a photon strikes a bound electron, is the energy above the work function? If the answer is yes, if it's above the work function, the electron absorbs the photon. The photon essentially dies. Its energy is transferred to the electron becomes free. If there's leftover kinetic energy, you'll have kinetic energy and it'll move. If it's below the work function, the photon is not absorbed and it's going to reflect off the material. Now, for our formula, kinetic energy is equal to HF minus phi, and phi is the letter we use for the work function. So leftover kinetic energy is equal to the incoming photon energy minus the work function. And again, the work function is the ticket price. It's what it takes to remove that electron. And any leftover kinetic energy becomes current. It causes the electrons to move. So if I just meet it, they're free, but they're not moving. I need something beyond that to cause them to move. Now, things that use the photoelectric effect, solar panels, clearly, they generate electricity directly from light. The other thing are photocells. Now, where you might have a photocell is if you have a garage door. It's a safety feature put on all new garage doors, in which there's a beam of invisible light, you can't see it, that's going across the bottom of the door. That way you can't close the door if there's a small child or something in front of where the door is. It will not allow the door to work at all, because on the other side there's a photocell, and that photocell detects the light. If it does not detect the light, the door will not close. If you have one of these at your house, just try covering up that, putting something in front of it and try and close the garage door. It shouldn't close. And in the past 7 or 8 years, that's pretty much a common thing. It's also something they use in grocery stores and stuff like that. I like theme parks. Even theme parks now are using it instead of a turnstile. Some places you go through and you break a photocell light, and it counts as whether or not somebody's going onto the ride or not. So a photon strikes a metal with a work function of 2 electron volts. If the emitted photoelectron has a kinetic energy of 3 electron volts, what is the energy of the incoming photon? Well, K is equal to HF minus the work function. The incoming photon is HF. So HF is equal to K plus the work function. So in this case, it's 5 electron volts. Now, the other thing I might want to know is, what is the wavelength of the photon that's coming in? Well, now I'm going to say E is equal to hc over lambda. I'm looking for lambda, so it's hc over E. Now, since I have electron volts, use the electron volt hc value. 1240 electron volts times nanometers divided by 5 electron volts is equal to 248 nanometers. That is not visible. It's outside of the visible range. 248 nanometers is outside of the visible range. The visible range is 400 to 700 nanometers approximately. So the cutoff frequency. The cutoff frequency is essentially the ticket price. It's the frequency that is just equal to the work function. The K is 0. In other words, I just have enough energy to remove it, but not enough so it moves. So if I set K equal to 0, then HF minus phi is equal to 0, so therefore HF is equal to phi. That's where that equation comes from. What is the cutoff frequency if the work function is 3.5 electron volts? Well, K is equal to HF minus phi, and K is 0. So therefore HF minus 3.5 is equal to 0. So therefore HF is equal to 3.5 electron volts. But I'm looking for F, so now I have to divide by H. Since I'm given electron volts, I use the electron volt value for H. And I get 8.4 times 10 to the 14th hertz. Above that frequency, I get electric current. Below that frequency, I get nothing, not a zip, nil, bupkis. So if you increase the intensity or brightness of a light, what does that cause to happen? So if we just make a light brighter, E is equal to NHF. Well, I'm not changing an individual photon. I'm just adding more photons. So N actually increases. Or total energy also increases. But remember, if I don't have enough energy per photon, I don't get any electrons emitted. Now, if you increase the frequency of a light, now what we're now doing is increasing an individual photon. E is equal to NHF. Now I'm increasing F, so therefore I'm increasing each individual photon's energy. Yes, I'm increasing the total energy also because the photons are going up, but I'm causing the individual photon energy to increase. That could lead to electric current.